Hi everybody. So today I'm going to talk about mostly about assignment 3 stuff. So first of all, how do you feel about assignment 2? Is it okay? Yeah. So everybody got 80 points? How many did you get? 80. Good. You guys? 50. Not bad. You? 76. How come? Oh, okay. Better call? Yeah, okay. So which is the difficult part you feel about assignment 2? Exact. You?
Yeah.
Exact. How about fork?
No, fork is your.
Fork is okay. Yeah? You guys? Fork? No? Yeah. So so this is what I told you about roughly more than a month ago. So at that time, I was in recitation, and the deadline for assignment 2 is still March 13th. So now, after that, Jeff postponed the deadline to by 3 weeks, and which is this Monday. And at that time, I said you get enough time for assignment 3, which is not the case now. You only get like less than 5 weeks, which is basically a little more than a month. So you really need to hurry things up. And I believe after assignment 2, you get a better idea of what an assignment looks like, right? It's not some toy assignment just at night of deadline, just brush up for a few hours and get it done. It's not the case, right? So you really want to get started earlier. And so here is an overview of assignment 3. As usual, we have 7 code reading questions. There was 40 points in total. And also, as usual, I would recommend you to just leave them alone for now, so you can get back to them when you start coding a bit and get a better idea of what the code base looks like. So again, we have a design document, which was 60 points. Basically, to be honest, these 60 points are given to you actually. So you can't be wrong with them. So you just come up with a rough design document, submit them earlier so we can grade them. And now you get back, you see the list, right? The magic list. Now, according to that list, you just need to discuss every bullet. Then you get the points. So basically, these 60 points are given to you. Just remember to submit the design document earlier, so we can grade them, so you can get a chance to submit a second copy of it. And for what? Okay. So for the implementation, it was 100 points. As Jeff said about today, if any of you decided to take the solution set, 50 points will be deducted from this 100 points. So any of you plan to get the solution set here? No? Yeah. You know why? Because people come to recitations to get high scores, so you don't need to get the solution set. Yeah. So, so for these 100 points, we have various tests. Each of the tests worth a few points. So for first of all, we have a call map test, which will basically test your k-malloc. So this you should be able to pass this test after you got your call map done. And then we have basic user program test. This is the same with assignment 2. So your virtual memory system should be able to run some basic user programs like bin true, bin false a couple of times. So this part you can pass it now because you have dumb VM, right? These 10 points you can get if you submit a patch right now. But after you change it to your own virtual memory, I'm not sure you still can get these points. And also for malloc test, we have this test program. It's just worth 5 points. And this will test your SPRK syscall. So in assignment 3, you need to add one more syscall called SPRK, which will basically change the heap size of the virtual memory system. And then we have a bad call, random call, and crash. So you are familiar with these two. Bad call, we test all kinds of bad arguments, and random call, we just randomly test all the syscalls. It serves as a stress test. This crash, there's something new with this crash test. So first of all, remember that before, when the user tries to access some embedded memory, dump VM will catch that and will crash the current process or current thread elegantly instead of crash the kernel, right? Now you need to handle that. So when the user tries to access some embedded memory like 0x4 million, you need to catch that and return some error in your VM fault handler, so the kernel can kill that process properly. And also for crash, there is a test which is basically do an infinite recursive call. That basically will increase the stack size infinitely. So at some point, you need to decide that, okay, this is enough. If your stack size is this large, that means the user behaves very badly. You need to terminate it. So there's two things new here about the crash test. And for so the assignment 3 works in 2 stages, right? So in first stage, the very first stage, you need to get your call map down. This is the most simplest part. And then for the first stage, we'll give you enough memory. So you will have like 16 megabytes of memory. So you don't have to consider what if you cannot find a physical page to allocate. You don't need to consider that case. So first of all, we'll give you enough memory. You need to make sure that your virtual memory system can run these programs given sufficient number of physical pages. So we have a matrix multiplication, sort, and huge. This test, I believe the altogether will give you at least 8 megabytes to run them. So for those who working alone, you need to pass this. And then also for the first stage, we have single process test, which is this, and also multi-process test, which is triple each of them. So for matrix multiplication, we have triple mat. For sort, we have triple sort. For huge, we have triple huge. So basically, it will run 3 copies of the program and stress test your virtual memory system. Still, at this point, you still have enough memory, so you don't need to do swapping. This is the end of the first stage. And in the second stage, so so there is also a parallel VM test in the first stage, non-swapping case, which will stress test your synchronization in your virtual memory. So this parallel VM will create like 20 or so threads to 24 threads to run. So you really need to protect each of your kernel data structures very well to pass this, to synchronize them properly. So this ends the first stage, and after that you want to consider what if you don't have enough memory? What if when you try to allocate the physical page, there is no physical page to allocate? So at that time, you need to choose a victim and kick out that, actually swap out. You cannot just discard that physical page. Swap out that physical page and use that physical page, okay? So for this test, I think the altogether will give you 1 megabyte of memory, right? To run all the tests. So we have a single process test, which is basically sort, huge, and matrix multiplication. We have multi-process test, triple each of them, and finally we have a parallel VM test. So for those who work alone, you don't need to pass these swapping cases. You're done at this point. You need to only do the first stage. So for those who work in groups, you need to make all of them working. All right? Any questions so far? Yeah.
You said that the swapping ones are the same ones as the non-swapping ones? So
Yes,
we just change our memory?
The same. What do you mean? They're the same code actually.
Yeah.
The same user program.
So in order to test that, we just give ourselves a limited amount of memory?
Yes. In order to test that, just change the 06161 configuration and change the memory size to test that. Okay. So what you need to do is actually, so this page describes what will the autoweather test, right? And what you need to do is to first design and implement the address space, or more roughly the virtual memory system. So you need to figure out how to manage the physical pages, which is basically the COMAP does, and address space, mainly the page table. You need to design the format of the page table, either use a dump linked list or use some fancy multi-level page table. And for the address space, you have a family of AS_scope functions, right? AS create, destroy, copy, define region, define stack, all of them. You need to write all of them. And the TLB, so we know that in MIPS or in this OS 161, we adopted a software managed TLB, which basically means that you need to manage all the TLB entries. You need to choose which one to load the TLB mapping. You need to choose which one to kick out, to swap, to load a new memory mapping. And also finally, swapping part. And additionally, you need to implement this SPRK syscall to pass the malloc test. This SPRK syscall is basically the interface between user space malloc and your virtual memory system. Okay, and so here's a few tips to approach this assignment. So first of all, after assignment 2, I believe you're not panic anymore, right? You kind of know what's waiting for you, and you need to read a lot, including read the code, the existing code, mainly the dump VM, some online materials, and you need to debug a lot. And also for starters, you can study how dump VM works, because so far dump VM works fine, right? It can run, given sufficient memory, it can run basically any programs. So you can run triple huge, no problem, as long as you have enough memory. So you want to study how dump VM works to basically borrow some ideas from it. And then you want to work on COMAP first, because this is the basis of the virtual memory system. To build a virtual memory system, you need to figure out what pages are there for you to manage, right? What you need to do when you want a physical page. What do you need to do when you are done with a physical page? So this is basically managed by the COMAP. So this is also to pass the KM2 test. And then address space, VM fault, all kinds of that. And then finally swapping. So this is basically the roadmap to how to approach this assignment. So today we're going to talk about what is COMAP, and the user address space layout, and the TLB in MIPS or 6161 simulator, and how dump VM works. Okay. So first of all, what is COMAP? So basically, COMAP is the physical page manager. So it's manage all the physical pages, right? So it's basically the data structure. You have some data structure to maintain the status of each page, so you know which page are free, which page are not free, which is dirty, which is clean, and all that. So, and you have a set of operations to operate on this data structure, which is the interface of COMAP and other parts, right? So the interface of COMAP is that it's kind of simple actually. So we have two interfaces: allocated K pages, which is basically, as the name indicates, give you some physical pages, and free K pages. So although it may seems simpler, this function can be very tricky actually. So think about it. You want to allocate a physical page. So you scan some array of page status and found an available page, right? Given that you have an available page. But what if you don't have an available page? You don't have a free page. All the pages are occupied by some process or the kernel. In that case, what do you need to do? Swap out. Or you can just panic, saying that I have run out of memory, but you won't pass the test, right? So you need to figure out which test to kick out. And to kick out that page, you need to actually modify the other process's page table and TLB entry, because that page could be actively accessed by other process, right? There's another process maybe accessing this page. Now you decide to kick out that page. What happened? So you need to kind of stop that process and flush this page into disk and change that process page table. Now you have this free page. But what happened in the other process? The other process will feel like, oh, suddenly the page disappeared. And then what if the other process is about to access that page? You need to immediately swap in, right? So these two functions, this one, especially this one, is not very simple actually. But in the first stage, it's okay. Because when you want to allocate some pages, you always have the pages. So you don't have to do the swapping. And for when you design the call map, you want to ask yourself a few questions, right? So what information should you maintain for each physical page, right? The minimal information should be the status of the page, right? You want to know if the page is available or not, right? Is that enough? Address? What kind of address? Physical address? Physical address? Yeah, physical page, yeah, that's one thing. Well, it's kind of tricky because you can actually not store that information in the page structure. You can compute it. Yeah, but yeah, that's something you need to think about the physical page. So we have physical address, we have the status. Is that enough?
Which processes?
Yeah, which process owns this page? So that in the future, in case I want to swap out this page, I need to notify that process, right? So who owns this page? What else? Clean? Yeah, that's basically the page status, right? Clean, free, dirty, something like that.
Why do we need to notify the process? If dump VM is asked next time for the page, it will swap in, right? So why does
Dump VM, there is no swapping in dump VM.
I mean, yeah, our new VM.
New VM, yeah?
Responsibility of VM, right? I mean, process did not know that it is.
Yeah, I say notify, not like sending a message. You need to change some of your data structures or some information to let that process know that this page is no longer there, right? You cannot just swap out that page without letting that process know. Otherwise, that process will think, oh, this is still my page. So now two processes exist in the same page, right? So basically, we have physical address of the page, of course, because this is a physical page. We have address. So who owns the page? Basically, the owner information, right? We have the page status, and maybe you will need other information as you go, as you get started and design the call map. And also, how do you synchronize the access to the call map? So first of all, why do we need to synchronize? Because the call map is system-wide information, right? All the processes on this CPU or on this system share the same physical memory, share the same call map, right? What if two processes want to allocate some physical pages at the same time? Right? You definitely need to synchronize the access. Actually, synchronization is the most difficult part in this assignment. It's less obvious in the first stage because you have no swapping. Actually, everything is pretty fast. You don't have the resting conditions. But once you have swapping, the synchronization will be a big headache of you. But that's a long story. So to basically, you want exclusive access to these call map structures, right? So a lock will be a best fit. You have one lock to protect the call map. Whenever you access this call map, you want to query or you want to allocate some pages, you acquire this lock. So that's kind of simple. And what to do there if there is no page available? Either panic in the first stage, or you need to swap out some pages. So, and in terms of swapping, there is a whole scope of swapping algorithms, which page to swap, right? You need to consider all that in the second stage. Any questions so far? Everything's okay with this call map stuff. This is quite simple actually. It's just to warm you up with the virtual memory system. So secondly, this is, you want to know what exactly is what does it mean by address space, right? We have talked about this in class, and here is the output of file only test. So first of all, this file is ELF format, right? So we can run it in the manual. What the manual really does is using a function called load ELF to load this binary file into the address space, so this program can run. And inside this binary file is in a special format called ELF, and it defines a few regions. So actually here it defines 3 regions. So this, you can use this and with -p option to print out what regions are there for any ELF format files. So you have bin true, bin false, test bin better call, whatever test. Here I use a file only test for example. So we have 3 regions here. The first region is kind of a dummy region. It's not actually code. It's just some MIPS segment information. So you can ignore this. This is the 2 interesting regions. So the first region, the starting address, virtual address, is this, right? You may be very familiar with this address because it's where the user program starts. And ignore this physical address because when the GCC compile the source code, the compiler doesn't know actually where the physical address will be. So it just set this physical address the same with virtual address. So it's this virtual address that matters. And here is the region size. So for each region, we have a starting virtual address, the size of the region, and the flags. This flags basically means the permission of this memory, right? This Rx means it's readable and executable. So what's this region? Code region, right? It's readable and executable. And now we have the second region, this, starting from here, and memory size is this. The flag is read-write. So what's this region? Data segment. The static, basically the static arrays you declared will go to this region, right? So this is the 2 regions. So we can see here the file only test has 2 loadable regions. The first region is not loadable. It's just to keep some meta information about all these files. So we have 2 loadable regions, and I guess most of the files here in test bin or bin have 2 regions. So you will need to consider this when you design your address space, because when you load a address space, when you load an ELF file, it's not necessary that that ELF file has 2 regions. It may have 4 or 3, so it may be a flexible number. So it will be clear when we talk about dump VM, how dump VM maintains this region information.
What about stack?
Stack? Yeah. Stack is runtime's region. It's not compiled, it's not static, right? So when you compile a file, there's no stack yet. So when we load this ELF file into address space, you need to set up the stack. So at that time, the stack appears. At this point, there is no stack yet. Okay?
Is there overlap from the first region and the second region?
There what?
Overlap. So first line, the V address is 0 and
actually, this is kind of a virtual region. Yeah, so there is no data here. So the code goes here, the data goes here. Here, I believe, I don't know exactly, but I guess, you are welcome to do some research on it, but my guess will be there's some symbol information on this. It's interpreted by the loader, the ELF loader, not the actual some stuff you need to store in the memory. So this is the region type. Load means you can load this region directly into memory. Other than that, this is the region type, some very strange region type. It means, I look into it means the macro says MIPS seg, but I don't know what exactly it does it mean. Yeah. And also, if you look at the LODELF code, you will see that LODELF will only look for the loadable regions. LODELF will ignore this region. Okay. And okay, so here is the address space. Any questions so far? We're all good? Okay. Now, this is a more detailed version of the segments. So first, we have all kinds of regions. Inside one region, we may have different kind of segments, right? So for example, here, we have a text region, which is actually the code here. So contents, allow read-only code here. And we have read-only data in the same region. Note that this address is still smaller than this region start address, right? So in the first region, we have two segments. The first is the code, and the second is read-only data. So question, why do we put these two segments into one region? What is the read-only data? What? What is read-only data ESP? No. What? No. Read-only data. What? Not exactly. You can write it. Constant value. Yes, exactly. So, for example, you can declare strings in your C file, right? You can write code like character star A equals to hello world. That hello world is a constant string. It cannot be changed, right? So it's read-only. It's called read-only data. And now we know what is read-only data. Why do we put these two segments into one region? What? Not exactly. What does that mean? So the reason here is because both these two segments are read-only. So we can, of course, define different regions for this, but because they are all read-only, it's convenient to pack them into one region. So when we load this segment into memory, we can set their permission to be read-only altogether, right? And here we have data, this especially the same reason. So we put data, SPSS and BSS into one region here, because they can only be read and write, right? So, I don't know. Yeah, I believe you can search this on Wikipedia, but I don't know exactly what does it mean. So data is one of the BSS and SPSS is the static global variables. I don't know what the data is. So this is a detailed view of all the segments inside the address space, right? So we have code, read-only data, writable data, and all that. So here is what the user address space looks like, right? So because this is a 32-bit machine, we have from 0 to 4 gigabytes. This is the whole address space. And here, starting from this address, we have one segment, which is read-only segment. It contains the code and some read-only data, okay? And then, starting from here, we have a data region. How do you call it? Writable region, which contains several data segments. So these two are defined and it is contained in the ELF file format, right? So we have these two regions in the file, and then the function called load_elf, we load these two segments into the memory, okay? But what the load_elf doesn't do is that we know that for a program to run, the program has to have a heap, so you can do malloc. So all the malloc memory will be in here, and also the program also needs a stack. This is defined dynamically when loading this ELF file into the address space. And after that, so from this point up, This is all kernel. It cannot be accessed by user. Okay, this is what the user address space looks like. This is, of course, this is for file-only test. Other binaries or other ELF files may have different addresses. So in dump VM, there is no heap, actually. So you cannot run some program that contains malloc because there is no SPRK syscall. User space malloc won't work. And you need to define this in your address space. And for the stack, dump VM will just use a fixed size stack. So dump VM, when you load this ELF into the address space, dump VM will allocate a fixed size of, I don't know, maybe 16 pages as a stack. And from now on, yeah, how many? 12 pages for the stack. And then the stack is fixed. It never expand. Any questions so far about this address space layout? It's very important for you to understand this to implement the address space correctly, especially an ASST3 region. Yeah.
What is the malloc in lib density? There's one user lib.
Yeah, there's a malloc function.
Yeah, so it doesn't do right now? Doesn't work right now?
Doesn't work. You can try run, which test contain malloc? Okay, you can run malloc test and see. Yeah, because you don't have SPRK. There is no way to manipulate the heap, right? And so how does the dump VM handle all those address space stuff? First of all, let's take a look at the address space definition of dump VM. So actually, it's quite simple. So because we have two regions, we have two set of base and pages. So first of all, for example, this is for the first region. We have the base virtual address, base physical address, and how long is the region, how many pages this region contains. And for the second region, we have base virtual address, base physical address, and how long is the second region. And then we have a stack base. Basically, in dump VM, this stack base is a fixed value. So in dump VM, given a virtual address, how does dump VM translate to a physical address? First of all, how does the dump VM know if a virtual address is valid?
About 4 tenants.
Look at this when you answer. What?
If it's above 8, 8.
Yeah, if it's above this, it's definitely invalid. That's trivial. So given some address that's below this OSX meeting, how does dump VM know if that's a valid user space address?
See the base plus size if it falls within that.
See the base and?
See the base and see the size.
Mm-hmm.
It should
So,
be between those.
yeah, so the question is, given a virtual address, determine if this virtual address is valid. How do you do that? Well, in dump VM, this is vbase 1, right? This is vbase 2. And this is n pages 1 and n pages 2. If the virtual address falls into these regions, it's valid, either code or data, right? If it's not fall into any of these two regions, then dump VM know, well, this must be an embedded virtual address, right? Because it doesn't belong to any regions. And because a dump VM doesn't have heap, they could not possibly be here. So if you fall into any range here or here, this gap or this one, dump VM will know that this virtual address is not valid, right? Yeah. So basically, this validness check is done where? Where does the dump VM need to check that? Yeah, when user access that virtual address, right? If there is no TLB translation in the TLB, you will get a TLB fault, right? Dump VM need to handle that fault. First thing dump VM need to do is check whether that user virtual address is valid. If it's not valid, dump VM will not set up the TLB. Instead, dumpVM will return some error. So the kernel will know and kill the current process. Right? Otherwise, dumpVM will change the TLB entry to set up the mappings between the virtual and the physical address. Any questions about this address space data structure of how dumpVM maintains the region information and how does the dumpVM check if a virtual address is valid? Everybody got it? Okay. Now,
Sorry.
yeah.
The two regions, why is fixed, why is third?
Oh, I mean the fixed number of regions. Yeah, it's fixed number of regions too. Yeah. So actually, I checked several binaries in TestBin and Bin. All of them had 2 regions. So it seems nobody has more than 2 regions. Yeah.
In our structure, this will have to change, right? This is for dumpVM.
This is for dumpVM, and it works fine. It's your choice to change it or not. You can still use this. As long as there is no more than 2 regions, you're fine.
But stack will be not fixed.
Yeah, stack will be not fixed because you don't have so many pages to waste. Yeah. So, well, you have basically a different kind of options. First, you can still use this part as this 2 region design and add some other stuff you need. Or if you're not comfortable with this 2 fixed number of regions, you can use a linked list to maintain the region information, right? So you have various number of regions available. And also, you definitely need to add one thing to the region information. So instead of just maintain the VBase and PBase, actually you need to change this because dumpVM assumes each region is mapped to a continuous physical page, which is not the case in your virtual memory. So you need to change this anyway, right? Yeah, and beside that, so instead of maintaining a virtual base and how long is that region, you also want to record the permission of the region, right? If this region is read-only or executable or can be read-write, you can. This is because this matters because when you're swapping, you want to first swap out all the clean pages, right? To know if a page is clean, how do you do that? So initially, when the pages are loaded into memory, all the pages are clean, right? Once the user starts touching the memory, it becomes dirty. In order to capture the touching event, how do you do that? How do you know if user starts to write to some location? TLB fault. But if in the first place, if you set a TLB to be read-write, when the user writes to the location, you won't get a TLB fault. Right? Yeah. So
First write, you change the TLB from read to read, right?
the question is, how do you get the first write?
You mark it as read.
What?
You mark it as read the first time.
Mark
Mark as only read first time. So initially you set up everything as read.
Yeah, initially you set up everything as read-only, right? So once the user tries to write to the page, you get a TLB fault, then you can check the permission. If the page is read-only and user tries to write to it, you need to return some error because you are user not supposed to do that, right? But what if the region is originally can be write, is writable? Now user try to write it. Now you can just enable the write, but you also record that this page becomes dirty. Now when you're swapping, it may help you to make the choice which page to swap out, right?
Why do we need to keep track of this dirty and clean? Do we need to keep a page both in memory and hard disk so that the swap is faster? Do we need to implement that as well?
What do you mean?
Clean pages,
Yeah.
do we copy only when it has to be swapped out, or do we copy earlier and so that in case something has to be swapped out?
I would say don't swap out unless you really need to swap, right? So initially all the pages are clean, and some user when some touch them, some of the pages, you got some clean pages, some dirty pages, right? And when you want to swap some pages, you want to know which page to do. First, you want to choose the clean pages, because if it's clean, you don't have to flush the content to disk, right? But one trick is, actually I was wrong before. So when all the pages are loaded into memory, what's the status? Is it clean or dirty?
Dirty.
It's clean. So when you want to swap out that page, you can just discard it.
Yes, because you can load it from the ELF again.
No, at that point you don't have the ELF again. When the program is already running, you don't know whether the ELF is. Mark it is dirty because that page don't have a copy in the disk, right? Dirty is defining that the content in the disk and the memory is different. At that point, the content in disk is empty, and there is some content in the memory. So they're different. So now the page is dirty. So at the first, every page is dirty. Now, when you start flashing, it's basically a design choice. You can have a background thread to periodically flush all the dirty pages into disk, or you can do flushing only when you need to. Yeah, it's based on the design. And for the virtual memory interface, so first of all, which part of the kernel needed to interact with the virtual memory system? Right? So you already have done that in assignment 2. You call AS copy, you call AS create, maybe in exec-v. Yeah. Oh, it's a typo.
Like we call.
Yeah, you call all the functions.
Yeah.
You don't call this, right?
Yeah.
It's called by load elf. Yeah, you call it. Yeah, but you don't write the code to call them. Yeah. So this syscalls or system kernel functions interact with the virtual memory system. So in run program, you create address space for the current process or thread, and in load elf, you call these functions to tell the virtual memory system about the region information. And you also call AS-define stack in exec-v to get the stack pointer, and you call AS-copy in fork. So you have done that already. You have interacted with the virtual memory system. Now it's the time to write these functions on your own. And what does this function? So basically, the semantics of these functions are quite clear, actually. The name indicates what it does. So any questions about this? I mean, for example, you don't know which function, any function does what? They're actually quite clear, actually. So now, what's the virtual memory interface to user? Right? How does the user process interact with the virtual memory system? Basically, normally user don't see them, right? Only when something bad happens. Bad means there is no translation in the TLB. User has to raise a software interruption to notify kernel to fill the TLB. So user interact with the virtual memory system through 2 ways. One is TLB fault. This is the most common way. And this is without the user's consensus, meaning that user actually don't want to trigger TLB fault. User trigger TLB fault because user has to, right? User need to access a memory which is not in the TLB buffer. And also another one is SPRK. So this is actually a syscall. So user call this syscall when the user want to expand the heap information, the heap size. And so about heap, one question is, how do you decide where the heap starts? So when you load an elf into memory, you have this segment, you have this segment. You don't have heap, you don't have stack. But you know stack starts here, so you can set the stack pointer to be this value and grow downwards. But how do you decide where the heap starts?
The data segment doesn't grow, so you can immediately start sometime after that.
This segment?
Yeah.
Yeah, that's basically exactly how to do it. So you can, so when you load all the regions, you can know where is the last region and this address, right? Basically, you can set the heap to start from this address and grow upwards. So in your address space, you need to maintain the heap information. So where the heap start, where the heap ends. So initially, the heap size is 0. So heap start equals to heap end, right? Now, when user call SPRK, you need to adjust the heap end so your heaps expand. About SPRK, another thing, yeah, it's some later stage stuff. So I will discuss them in the next or probably next recitation. Anyway, so finally, what about TLB? So in MIPS, it's software managed TLB. Specifically in this OS 161, we have each CPU core has 64 TLB entries, each software managed. So it means that you need to manipulate the TLB entries by yourself. And the system do provide some interfaces for you to change or modify or query the TLB. So first of all, we have TLB read, right? They basically allow you to read one entry from the TLB. You can tell this function which TLB entries to read, right? Each TLB has an index from 0 to 63, right? You can read any of them. And you have a TLB write to write the content. Basically, you can set up the mapping between the virtual and the physical address using this function. You can specify which entry to write. And you have TLB probe. Basically, it allows you to query for a specific virtual address. Does the TLB contain the translation for this virtual address? Right? It is mostly useful when you want to kill the mapping, right? So when you swap out a page, you want to kill the mapping between the virtual address and this physical address, right? So you can use this function to query if the TLB contains the mapping for this virtual address. If it contains, you want to kill it. Otherwise, just ignore it because there is no mappings in TLB anyway.
What's the difference between read and probe?
This one? For read, you tell this function which entry to read, so you know which TLB to read. For probe, you don't know which entry it is. You just provide the virtual address, and you call this function. It will return you an index, either an index or -1. Right? And TLB random will just randomly pick a TLB entry and write the content to it. It can be used in a random TLB replenishment algorithm, just to randomly choose a TLB entry and write to it. Okay? Any questions about TLB? You can see this file for more information about the TLB. Okay. So what to do when you have a TLB fault? So user starts get running, and now all of a sudden user access some either valid or invalid memory, and you have a TLB fault. So the first thing you do, you want to make sure that this fault address is valid. Otherwise, you don't have to serve it at all, right? How to check if it's valid? Well, first of all, this fault address has to be in the user space, has to be in some of the defined regions, and the process has to have the permission to write to it if it's a write, right? Normally, all the regions are readable, but some of them are writable, some of them are not. So you need to check all of this to make sure the address is valid, and then you may need to allocate a physical page if you need. If it's the first time the user accesses this page, so for example, user just call malloc, which calls SPRK to expand the heap size. So user should have that page, but that page is not allocated yet. So when the user tries to access that page, he will get a TLB fault, and you need to allocate the physical page for it. And after the page table, so you need to maintain the mapping between the virtual and the physical address, and also update the TLB. Otherwise, user can still not access the memory. Right? This is basically the flow of the virtual TLB handler. So it's this part that can be tricky, because when you try to allocate the physical page, again, you might need to swap out. So all that headache. So how does the dumb VM handle the TLB fault? So first of all, dump VM need to check the full address. Right? We have already discussed this. It's quite simple actually. Dump VM just need to see if the fault address falls into one of the regions. If it falls into the region, then it's a valid virtual address. If it's not, then it's the invalid virtual address. And allocate the physical page if needed. Dump VM doesn't need to do this because dump VM has already allocated all the pages. Let's speed up a little. So after the page table, dump VM doesn't need the page table. And after the TLB, this is the code that's after the TLB. So SPRK syscall, we have discussed this. That's pretty much what I got for today. Questions? No?
So we should start with call map first?
Yeah, call map first. Yeah.
Exam day.
What?
Exam day.
Oh, exam day? Wow. Looks like I should end it earlier. You guys? Yeah. Do you need the projector?
No.
Oh, okay.
I'll take care of it.
Thanks.